Hi folks, I'm going to try and go through some bits of this component one paper for you. I'm only going to do the bits that are sort of requested by people in the feedback form. So if there is a particular question you want me to go through, I will do that. I'm not going to go through the entire paper question by question because it is rather time consuming to do that in a way that is going to be useful. A word of warning, I haven't really seen this paper. I've seen it, but I haven't done this paper before, and I have deliberately avoided looking at the mark scheme. So I'm kind of going to be looking at these questions fresh, talking you through my approach to them, and then I'll look at the mark scheme and try and sort of make sense of that and award myself some sort of mark for them. And hopefully that'll be a useful thing. The only question so far that people have requested is question 7, which must be near the end of the paper. So I'll find that and I'll go through that today. But do bear in mind, if there is another question that you'd like me to go through in a video like this one, I'd be happy to do that if people request it. So, okay. So question 7, thermodynamics is what we're looking at. The first part of this question, state what is meant by heat Q entering a system, and this is worth 2 marks. So in general, heat is, as a phrase, is what we use to describe energy that is thermally transferred. It is not, contrary to sort of it's a popular misconception that people think that heat is the energy that something has within it, stored within it, due to thermal vibrations and things like that. That we refer to as internal energy. So the heat entering a system I would describe as energy that enters, energy that goes into something by a thermal mechanism, so either by conduction, convection, or radiation or something like that. And hopefully that's enough. There's 2 marks for this. My suspicion would be that energy gets you that first mark, energy going into the system. And the second mark is for sort of classifying the type. If I was doing this in an exam, I'd probably go a bit belt and braces and go a little bit further than just saying thermally. To make sure of my second mark, I'd probably be saying either describing that process a little bit, saying it's something to do with conduction, convection, radiation, or something to do with the temperature gradient. Part B, then, we've got one of these graphs. This is a pretty classic setup, isn't it? We're hopefully all familiar with this type of thing. And we've got a gas being taken around a cycle. The arrows are so important in these. So this gas is starting at A, presumably it's going to B, then to C, and then back to A. This is important. The stage BC takes place at a constant temperature. So this is an isotherm from B to C. Calculate the work done by the gas in stage AB. So the things to bear in mind here, as always, we've got the change in internal energy of a gas is equal to Q minus W. Q, the heat put in, minus W, the work done by the gas. The other thing we need to bear in mind is PV equals nRT. So P times V is proportional to temperature, given that this is a leak-proof piston, so N is going to be constant, R is going to be constant. So the fact that BC is an isotherm means that the product of PV is constant along that line. Other things to look out for, work is equal to pressure times change in volume. And internal energy is 1/3 nRT. The total internal energy in the system is directly proportional to its temperature, which in turn can be determined by PV. So let's have a look at the questions then. Calculate the work done by the gas in stage AB. So this is work done by the gas because the gas is expanding along this line AB. And this is what we need to use. It's pressure times change in volume. So the pressure here, let's see, these are in kilopascals. That is 80 kilopascals. is the pressure, and the change in volume, this is 10 to the minus 3, so we've gone from 5 to 20. Times 10 to the minus 3, that's going to cancel with that. 10 minus 5 is 15, so 15 times 80 is 1,200 joules, I think. Hopefully I'm not slipping up on the arithmetic here. Yeah, and I think that's all we need to do there. That's going to get us our marks. Okay. For each of the stages, A, B, B, C, Ca separately, and for the cycle as a whole, use the first law of thermodynamics to explain whether heat flows into the system or if the system calculations are not required. This is the 6-mark QER. So, what the important points of this question? It says for each of the stages separately and for the whole cycle. Answering a question like this, I would be massively tempted to just label up at the side here AB, BC, CA, and ABCA, the whole cycle. And just basically address these absolutely individually. We're using the first law of thermodynamics, so if I scroll back up to where I scribbled this stuff down, there's our first law of thermodynamics right there. The change in internal energy is Q minus W, and we're treating each of these separately. So we're explaining whether heat flows into the system or out of the system. So let's have a look. As we go from A to B, we know that, I've just managed to rub all that stuff on. That was good, wasn't it? We know that, I hope that also happens on the video, that just disappears and comes back again. Otherwise, you're going to think that I'm going mad. I mean, perhaps I am, but not because of this. Where was I? A, B. We know that work is done, and we know the amount of work that's being done as we go from A to B. So let's have a think about the internal energy here. The internal energy of the system depends on the temperature depends on PV. This is constant pressure as we go from A to B, but the volume has increased. So in order for that to happen, the temperature has increased. Therefore, the internal energy of this system has increased. A quick rearrange of that first law of thermodynamics tells me that Q is equal to delta U plus W. Well, the temperature has gone up, therefore the internal energy has increased, and the gas has done work. So both of these are positive numbers, therefore Q is a positive number, therefore a significant amount of energy has flowed into this system. So I'm going to write this very, very briefly indeed, but what I want to say, basically, I'm going to head this with the first law of thermodynamics. Delta U is equal to Q minus W. Okay, so the first point I'm going to make is work is done by gas. Volume increases. But pressure constant. Therefore, internal energy increases. And perhaps I could put something. Internal energy increases since U is equal to 1/3 nRT. Equals 1/3 PV. Yep. So internal energy increases and work is done by the gas. Together, those imply that Q must be positive. So heat flows into system. Okay, next, BC. So BC, we're told BC takes place at a constant temperature. This equation tells us that if BC is taking place at a constant temperature, the internal energy remains constant. So what else is there to think about? We can think about work being done. There is a change in volume here, so work is being done on the gas. The internal energy, however, is remaining constant. So if work is being done on the gas, but the total internal energy is constant, then by this, heat must be flowing out of the system. So what's the phrase here? Constant temperature, BC. So that's my first point. BC occurs at constant temperature. So internal energy is constant. The volume decreases. So work done on the gas but since delta U equals 0, Q therefore must be negative. So heat flows out of system. Okay, finally then, CA. CA, there's no volume change here at CA whatsoever, so there's no work being done. So W is 0. The pressure is decreasing at a constant volume, and PV equals nRT. So a decrease in pressure at constant volume means a decrease in temperature, which in turn means a decrease in internal energy. So there's no work being done here. W is 0. However, the internal energy has decreased. So therefore, if delta U is negative, then Q is negative. Heat has flowed out of this system again. So no change in volume. Implies no work done. Decrease in pressure. Implies decrease in temperature. So delta U is negative. W is 0. Therefore, Q is negative, and heat flows out. Whole cycle then. Around the whole cycle, let's have a little think about this. Around the whole cycle, delta U has to be 0. We end up at the same place as we started. We start at A, we end up back at A, and therefore PV is the same as it was to begin with. So delta U has to be 0. We know that the gas is doing work, and the work done would be the area under this line as it expands. We know that work is then done on the gas as it contracts, and the work done on the gas is this much larger area. So more work is being done on this gas than the gas is doing. So there must be, given that we're putting work into the system, but there's no change in internal energy, that energy that we're putting in must be lost then as heat. So there must be a net flow of heat out of the system around the whole cycle. So I'm going to write delta U is 0 for whole cycle. Whoops, that's not how you spell whole. more work done compressing gas along BC during BC than done by expanding gas. Therefore, Q is negative and heat must flow out of the system. Okay, so let me just check that we've sort of addressed what we've been asked for. We've done the stages separately, and it is in bold, and we've done it for the cycle as a whole. We've used the first law of thermodynamics. We have explained whether heat flows into the system or out of the system at each point. So we've said heat flows into the system, heat flows out of the system, heat flows out of the system, heat flows out of the system. So I think we've addressed all the points. And it looks like that's the last part of the question. So hopefully my explanations of that made sense. The only thing that really remains is to check the mark scheme and see whether I've got it right. So let's just quickly do that. Okay. Oh, that's annoying. So I've pasted in the mark scheme, but it's sideways. Look. Yeah. Let's see. What am I even looking for? Question 7. Okay, so 7A. Sorry, I'm just going to have to slide this round to be able to read this. Yeah, so the 2 marks for 7A then, energy got us 1 by virtue of temperature difference. Okay, so a bit debatable whether what I wrote would have actually got that 2nd mark or not. Thermally might not have been enough for that. Certainly, I think if you'd mentioned a type of heat transfer, that would probably be enough for that. If you'd mentioned a temperature gradient, it would definitely. And then the next question, yeah, we got 1,200 joules, so that's fine. The 6 marker, which I'm going to assume was the bit that people were finding difficult. So AB, gas does work, we mentioned that. Internal energy rises, I believe we mentioned that. So heat flows in, Q positive, I'm pretty sure we mentioned that. BC, gas has work done on it, pretty sure we said that. No change in internal energy since the temperature was 0, we definitely said that. So heat out, yep, got that. CA, again, no work for that vertical line on the graph. Internal energy falls, we definitely mentioned that, so heat out, all good. And ABCA, the net work done on the gas. What? Oh, sorry. Yeah, there was net work done on the gas rather than by the gas. I think I phrased it as there was more work done compressing the gas than was done expanding the gas. No change in internal energy, definitely mentioned that, so heat out. So yeah, I think my answer hopefully would have got me up into this bracket. And remember that when you're answering these 6 markers, it's all about getting into a band. This is the way that they are marked. So you're trying to band your answer into the top band, and it's the physics in the answer that gets you into a particular band. So if we look at this statement that isn't in italics, they've considered Q, W, and delta U for all stages. That's what gets you into the top band. It's the stuff in italics that decides whether you're a 5-mark answer or a 6-mark answer. So there's a sustained line of reasoning which is coherent, relevant, substantiated, and logically structured. Notice it doesn't say it has to be in prose or anything like that. I think I'd be pretty confident that I did achieve that. I think my argument hung together, but what you're really looking to do is to get into the top band first, and that's where the physics is. So if we look at the 3 to 4 mark band, you've only considered 2 of Q, W, and delta U for all of the stages, or you've done Q, W, and delta U for most of the stages, but not all. So it's the physics that chooses the band, and it's the sort of quality of your answer after that, the sort of the structure and that type of thing that gets you to the top of the band or the bottom of the band. Incredibly, that has taken me 20 minutes. So obviously you guys don't have 20 minutes to formulate your answers to these things, but I was sort of taking my time and explaining it as I went. So hopefully that has been helpful. Don't forget, feel free to request another question either in the comments or use the feedback form or something like that if there's another question in this paper that you want me to go through. And do in the comments say whether this stuff is helpful, because if it is, I'll continue to do it, and if it isn't, I won't. Take it easy.